Let's talk about one of my favorite topics in ecology, and that's models. Models are abstractions or simplifications of some process or object that are of interest to us. There are many processes in ecology that are of interest to us because they determine the value of economic resources or represent problems that we're trying to manage in natural resources and in forestry. Let's look at a couple of simple models that help us understand the world that's around us. Now, the first one of these that I want to talk about is exponential growth. Exponential growth is one of the simplest representations of population growth, and it can be depicted in the following way. So we can say that the change in a population per unit time is a function of the reproduction rate of the individuals within that population, the per capita reproduction rate, how many new individuals are born from each individual adult, and times the total population size. Really simple, right? We've got two parameters, the per capita growth rate and the total population size. This model results in the following kind of dynamic. We've got time here on the x-axis and n, which is our population size. Pardon my horrible handwriting. And what's interesting, or what's very notable about this model is how it behaves once you start to plug in some information. So let's say you start some non-zero population number, and if you have a rapid growth rate, let's say a population that reproduces really rapidly, you'll have a steep growth rate. And then if you have something that's a little less rapid, but still rapid, you still have a steep curve here. And then we'll do something that's a little, that's not as steep, let's say, like this. In each of these cases, we've got the same general pattern here, which is exponential, non-linear growth. They're just occurring at different rates. Now, the problem with exponential growth is that it always goes up to infinity. Each of these outcomes is bounded by infinity, and infinity is a bad number. It does not play well with other numbers. It is a difficult thing to deal with, and mathematicians and physicists hate it, and so do ecologists. Once we get past a certain range here, we stop gathering useful information from this model. That's a problem with it, and that's results from it being so simple. However, in this range of the data, or this range of the model, its behavior here, it's still telling us something worthwhile. It's showing us how this relationship is changing over time, how this population is changing over time. And if we can measure this in the field, we can get an idea of how we should expect the population to change in the future. In fact, should we expect to see it growing very rapidly, or when would we start to run into some sort of resource limitation problem?